Here we're going to be talking about fluid properties. Let's begin by relating back to what you had dealt with in thermo. In thermo, you had dealt with something called the specific weight, the specific volume, which was basically the volume over some mass. Relate that back to your physics course, and somebody told you about, and chemistry as well, the density. Now, possibly they used the symbol of rho. If they did, then that's good, because that's what we're going to use in fluids. It's simply the mass per unit volume. As is the case, a lot of times different courses, here was chemistry, have the same thing as in common, but yet represented differently. Okay, in fluids, we're going to represent things. This is a rho, a density, in this way. Same way we did back in physics and chemistry, the mass per unit volume. However, let me show you this symbol here. This is, you've probably seen this before, but let's move this just so you know that there is a difference between the density and pressure. Very often people mistake the symbol P, which is pressure, which we'll get into later, for density. I can see why, because the two symbols look very similar. This is what the symbol typeset for rho looks like. But when we get into fluids a little bit, we have to consider how you might measure something like this. Would you figure out what the measurement for something like this might be? So with that, let's introduce another term which gives you some indication of how you might actually measure something. So there's a term called specific weight, and usually represented by the symbol gamma, which is nothing more than the weight per unit volume. Now this would be something that would be very easy to measure. You just come in, take a scale with some numbers on it. You take a beaker, say, or some type of container, 5-gallon bucket, 1-gallon bucket, doesn't matter. You take this bucket, you put it on the scale, you adjust a little knob here until it zeroes out, and then what you do is you fill it with the liquid. You fill it to a certain height. Of course, you measure that, and there's probably a radius. If it's a gallon bucket or a beaker, there's going to be a radius to it. You do something like that, then you're basically, with the radius and the height, what you're looking for is the volume. That's the projected area up here that you would see if you were looking down. And then the height, this would give you the volume of it. You'd read the weight off here, and just like that, you'd end up with the specific weight of it. Say this turned out to be 1 cubic foot, for example. I don't know what radius and height would give you that, but you can find that. If you had that, you put water in here, it turns out that water weighs 62.4 pounds per cubic foot. Now, at first glance, all right, that's great, but how does density relate to specific weight? And I'm going to put all this in a summary at the end. So if this is coming at you or looks different, just wait. We'll cover everything at the end, or review everything at the end. If the density is the mass per unit volume, then all I have to do is multiply this times the gravitational component, absorb the mass together with the g, and what you have is the weight per unit volume, because mg is just equal to the weight, or if you just like the term W, that's fine. That being said, that gives you a relation. That relationship is gamma is equal to rho times g. So in order to move from something you can measure to something you want to write down, as far as the density goes, you just take the 62.4, you divide that by 32.2, should give you approximately 1.94. Now, here's where we start looking at units. Remember, mass, if we're looking at the units we're mostly interested in this book, are SI and the British gravitational. So we're using slugs, feet per second squared, and then pounds. Same thing as F is equal to ma, because g is an acceleration, W is a weight. It just happens to be very specific that the acceleration is 32.2 here. That being the case, these units are slugs per cubic foot. These two numbers are something that you probably should remember because they're reference. And what do I mean by reference? Well, most of the Earth is covered with water. If you look at the predominant liquid that exists on Earth, it's water. Now, salt water, yeah, granted, it's different a little bit because its density and specific weight are not exactly these numbers, but pure water is. So the key is when you measure things, usually you're referencing them to water. So how do generally people reference things to water? And that's where a term called specific gravity comes in. Now, some textbooks list this as just an S. Our textbook, the one we happen to use at the moment, uses SG, but you might want to look. Some of them put a period. Some of them put a period here. Some of them don't, but you need to pay attention. There's no real Greek symbol for this that I know of. There probably is somewhere, but it hasn't been universally adapted, and it doesn't end up in fluids books as well. This is simply a ratio. It has no units. It is simply the ratio of the weight or density per unit volume of a liquid related to water. For example, take water and pour oil in it. What generally happens after you let it sit a few minutes, your oil kind of sits on top and the water sits underneath. So therefore you would conclude that this is lighter, weighs less, whatever you want to say, lower density, whatever. So you might be interested in, well, what's the ratio here? Well, it's very simple. You could come in and say, well, gamma. Now, the specific gravity has to be related to a particular liquid. So let's say the specific gravity of oil happens to be the specific weight of oil over specific weight of water at some reference temperature, because the density and the specific weight does change a little bit, and we'll talk about that in a little bit. But for the case in point, it's usually at 4 degrees centigrade, and it's usually this number up here. Now, if you look at this, you'll find that you could rewrite this in this way. And since the G's are the same here, you can cancel them out. So you have a way of referencing yourself, or referencing a liquid, back to the most common liquid in existence on the planet Earth, which is mostly water. So again, let's do a little round robin here, or create a little review of these three particular properties, which are all related to each other. If you have one, you have the other. First, you have density, which is just mass per unit volume. In one unit system, it's going to be slugs per cubic foot, and the other going to be kilograms cubic meter. Now, that's related directly to gamma, which is the weight per unit volume. 1 unit, pounds per foot to the third. The other unit system, newtons per meter to the third. Now, specific gravity is the relation of a, say, any particular fluid, say, happens to be the gamma of that fluid related to water, just the same thing as the density of whatever that fluid is related to water. Now, let's relate or figure out standards for these. If these are standards, then we need to know what these are. Generally, rho of water for that standard is 1.94 slugs per cubic foot, or some books will say this. I tend to like to use 1,000, but I think the reason I like to use 1,000 is because that is the basis of the creation of some of the units in SI. But we'll just stick with what is listed in a lot of textbooks, mainly 999, and it's kilograms per meter cubed. Now, for water, looking at pounds per cubic foot, or now if you multiply 999 times, of course, the gravitational constant is that, you'll get about 9810, but a lot of times that 1 will not exist there because they're picking 999 instead of 1,000. Sometimes I may put a 1 right here, but this is in newtons per cubic meter. So what might you be required to do here? Let me give you a case in point. Okay, first of all, these are standards which exist. So say someone created a table, SG, rho, and gamma. And say this table went down the page and someone just filled it out. And we're going to go through the process of just filling this in. 2.0, 13.6. This, by the way, is mercury. mercury is 13.6 times heavier than water. Let's say 0.7 slugs per cubic foot. Let's say 125 pounds per cubic foot and 7 kilograms per meter to the cube. Now, how do you fill out the remaining parts of this table? Well, first of all, anything in this column has no units. So if someone were to give you this table, they would have to specify what units they wanted to see in these. Did they want to see SI units or British gravitational? If someone didn't tell you which ones to use, you're open to use whatever you want. So let's go through the calculation here. And I will pause this and bring up the online calculator here. Alright, I've got a calculator here. Alright, so let's start with the 2.0. Now, what am I going to be multiplying this times? Now, when I touch this, the calculator is going to disappear, but I can get it back pretty quickly. I'm multiplying 2.0 times, let's say I chose to fill out this row with SI units. So, or let's say I chose to fill it out with both units. Okay, that might be more instructive. So 2.0 times the density, the reference density here. The reference density is 1.94 for one, and 2.0 times, I'll go ahead and stick with the 999 for the other. And let's see if I can get my calculator back. And whoops. Alright, so 2 times 1.94, so 3.9188. Okay, 2 times that is, I'll go ahead and do it, 999 times 2, 1998. So the answer to this would be, and I'll kind of stick it in here and truncate, 3.2. This was related to slugs, so slugs cubic foot, or 1998 kilograms per meter cubed. Alright, now how do I do the next? 2.0 times, I'll do 62.4, and 2.0 times 9800. This will give me, now these were the density, and what we're about to do here is the specific weight. So, two times 62.4, 124.8, 124.8, okay. Now what we're looking at is 2 times 9800. Well, that's a pretty big 1960. Now I'm not putting units here, but I'm putting them back in here. So if I put this in, it's 124.8, and the units on this come straight from here. That's pounds per cubic foot, or 19600. This times it's newtons per cubic meter. And so really what you're doing is you're filling out the columns. filling out the empty spaces here. So all you do is 13.6 times 1.94 gives you the number that goes right in here, and 13.6 times 999 goes in here as well. 13.6 times 120 or times 62.4 goes right in here, and so on and so forth. Now, what do you do with these? Okay, so this row gives you 0.7, and obviously if it's in slugs per cubic foot, you're in the British gravitational system. So what you do is you divide that by 1.94. That gives you SG. You put that right here, which if you wanted to see that, 0.7 divided by 1.94, 0.380, so 0.386. So what was it again? 0.361, sorry. Now you could do a couple of things. One is you could use this to move yourself over to here, or you could take this, take the 0.7 slugs per cubic foot. If you have slugs, you just multiply that times 32.2. That gives you 0.7 times 32.2 gives you 22.54. 22.54, and that gives you 22.54, and the units on it become pounds per cubic foot. Now why? That's because this is feet per second squared. Again, we're stuck in this unit dilemma. Let's grab this and pull it out. Slugs, feet, over feet cubed second squared. What is that? Well, F is equal to MA. Pounds is equal to slugs, feet second squared. So a slug is nothing more than a pound second squared over a foot. Put that back in this, and what you get, pounds second squared over a foot. And if you want to, you can put this in a square and get rid of that. So here you have foot squared. Now unfortunately you have foot squared, and you have another foot here. So pound second squared foot, this came directly from the slug. The foot squared came, and the second squared came from what was in here. That knocked that out, and so what you ended up with was pounds per cubic foot. So again, this is pretty important here for unit exchange here. So you start to see the idea. So you can fill out, if given any one of these, you can fill out any of these. For that matter, you could be given the 0.7, move over, find this value, and then use that 0.361 to find the gamma in a different unit system. So if you did that, you're multiplying the SG times gamma of water, and so if you did 9800, that would give you the gamma that would be equivalent to that gamma, but in a different unit system. This one would be Newton per meter cubed. So this has no connection to any unit system. It can move you in and out of a different unit system. Let me repeat what I'm saying. I took the density in British gravitational. I found this. There are no units here. It simply moves you from a reference point, mainly these reference points, to the actual values. So I can multiply 0.361 times this gamma or this gamma. It just seemed logical that if British gravitational was in this column, that maybe British gravitational would be in that column. Now let me do one final thing, and that is reference again in a more detailed sense of some of your other courses. As we talked about before, physics and chemistry started you off over using densities. And actually, chemistry may have started you off using moles. More than likely that was the case. I believe most people take chemistry before physics, but they can take them at the same time. And what generally happened is you were introduced to something like this. Now, temperature has the same units regardless. So does pressure, and so does volume. So your strange units come in here. R could be represented in several ways. It could have moles in the bottom of it, and so you need to put the number of moles out here. When you got into thermo, somebody started getting you and replacing that N with an M, and these units were the same, so nothing happened there. So in order to change this to, say, kilograms, for example, your R had to be changed. The units on the R's, in other words. So you had a bunch of units on top, but you had a mole underneath here. Well, now the R has to have kilograms in the bottom in order to knock it out. So this was your introduction to somewhere in which you made the progress from moles to, say, kilograms, and then someone probably said, well, let's do this. Where rho was nothing more than the mass over the volume there. So then a new property popped out. Now, what you have to realize is there was a thing called the universal gas constant back then, but now when you move into this, you may actually not have a universal gas constant. You may have a gas constant that probably was associated mostly with air. But there are other ones as well. So your introduction to density came through this process. Then you ran off to thermo. They flipped them over. They also did some crazy stuff to you that probably annoyed you because they'd stuck in there a pound's mass and a pound's force. So they went off and went to this English engineering system. So when you're in thermo over here, everything got switched on you. But you were still hanging around with the density. And then you ended up back over in here. In fluids, you're back to where you were before. Now, if you go in to a thermo table, and you could try this if you wanted to, and say you wanted to do the saturated liquid value at, say, 80 degrees Fahrenheit. And you went in there and you read off the volumes, specific volume. If you go over into the table in fluids and you read off the density at 80 degrees Fahrenheit, lo and behold, if you take that number, which is usually pretty small, put a 1 over it, you get the same numbers. So these are redundant. These tables are redundant. The only difference is in thermo you were interested in, if you were looking at P and V, you were interested in, they might exist out here as a liquid, but they also might exist somewhere out here as a gas or a steam or whatever you want to call it. So you're actually in fluids, you're going back to this area here that you visited before.